Hi, in this video we will derive the loss function for logistic regression. So logistic regression is a discriminative classification algorithm. Let's say we have only two classes. For discriminative classification, we will directly model the probability of class y is equal to 1 given our inputs x, or probability of class y is equal to 0 given our input x. But we do not need to model both of them because probability of class y is equal to 1 given x is simply 1 minus probability of y is equal to 0 given x. So if we calculate one probability, second is trivial. So to model probability of class y is equal to 1 given x, we use the following formula: sigmoid function of x transpose w, where x transpose w is nothing but x1 w1 plus x2 w2 plus and so on plus xn wn, where x1, x2 up to xn are input features and w1, w1 up to wn are the corresponding weights. So if it was a simple linear regression, our prediction would be simply x transpose w. But in case of logistic regression, we need to apply a sigmoid function because x transpose w is unbounded and can take values from minus infinity to infinity depending on the weights and values of x. But since we are modeling a probability of y belonging to class 1 and probability can always lie between 0 to 1, we will use a sigmoid function. So sigmoid function is a function as follows: sigmoid of input z is nothing but 1 upon 1 plus e raised to power minus z, or in other terms it's equal to e raised to power z upon 1 plus e raised to power z. So we can see that as z goes to infinity, as the input inside the sigmoid function goes to infinity, our sigmoid function tends to 1, become equals to 1, and as z goes to minus infinity, the numerator becomes 0 and denominator becomes 1, so the sigmoid function becomes equals to 0. So this is infinity, this is minus infinity, and this is z axis, and this is our sigmoid of z. And for z is equal to 0, we can see sigmoid of 0 is e raised to power 0, 1 plus e raised to power 0, which is 1 upon 1 plus 1, which is equal to 1 upon 2, which is 0.5. So for z is equal to 0, the value is 0.5. As z tends to infinity, the value tends to 1, and as z tends to minus infinity, the value is 0. So the sigmoid function looks like this. So to model the probabilities, we apply the sigmoid function to the input x transpose w so that the output value lies between 0 and 1, and we model this as probability of y is equal to 1 given x, and we try to train weight vector w in such a way such that we get the maximum accuracy on our dataset. So now the loss function is defined as follows: we have to maximize the accuracy, and to maximize the accuracy, we will maximize the likelihood. Now to understand the concept of likelihood, let's say we are given a random variable x and its probability distribution function fx. So likelihood determines that how likely it is that the sample that we have, the sample points x1, x2, xn, let's say we have n sample points, how likely it is that these sample points are coming from the random variable x and follow the distribution f of x. So we can clearly see that f of x1 is the probability of obtaining point x1 from a random draw of random variable x. So the overall likelihood that the sample points belongs to this distribution fx is nothing but f of x1 into f of x2 into f of x3 and so on up to f of xn. So basically, how likely is it that x1 belongs from this distribution multiplied by how likely that x2 belongs to this distribution and so on up to how likely that xn belongs to this distribution. So that's the concept of likelihood. And so what we will do in logistic regression is that we have defined a distribution as follows. So we have defined the distribution for our random variable y conditional on x. So it's a conditional distribution, and the distribution is as follows. Since the random variable is a discrete variable which can only take two values 1 and 0, so we say that probability of the random variable y being 1 conditional on x is sigmoid of w transpose x, and probability of y taking the value 0 conditional x is 1 minus sigmoid of w transpose x. So we have defined this distribution for y, and we want to train our weights w in such a way such that the sample we have, the training data we have, the likelihood of those samples in our training data to follow this distribution is maximum. So we would like to train our weights in such a way that the data we have, it is most likely that the data follows this distribution that we have just defined conditional on x. So let's say in our data set we have capital N data points, and the corresponding values of y for capital N data points are y1, y2, y3 up to yn. And let's say y1 is 1, y2 is 0 and so on. So likelihood is nothing but probability of obtaining y1, probability of obtaining y2 into probability of obtaining yn and so on. But probability of obtaining yi is conditional on whether yi is equal to 1 or yi is equal to 0. So if yi is equal to 1, the probability of obtaining yi is sigmoid of w transpose xi, and if yi is equal to 0, probability of obtaining yi is 1 minus sigmoid of w transpose xi. And we can write this in the concise form as follows, that sigmoid of w transpose xi raised to power yi 1 minus sigmoid of w transpose xy raised to power 1 minus yi. This is same as this complete expression, because if yi is equal to 0, then the probability of yi would be sigmoid of w transpose xi raised to power 0, which is simply 1, into 1 minus sigmoid of w transpose xi raised to power 1. So it reduces to 1 minus sigmoid of w transpose xi. And if yi is equal to 0, sorry, if yi is equal to 1, then this second term would be simply 1, because 1 minus 1 is 0 and anything raised to power 0 is 1, and this term would be simply sigmoid of w transpose xi. So this is just a way to write this probability distribution in a single line. So now the likelihood function becomes product of I is equal to 1 to n probability of yi, which is nothing but product of I is equal to 1 to n sigmoid of w transpose xi raised to power yi into 1 minus sigmoid of w transpose xi raised to power 1 minus yi. And now we have to maximize this probability, maximize this likelihood, and to maximize this likelihood, instead of maximizing this, we would maximize the log of the likelihood function, because since log is a monotonically increasing function, any parameters which would maximize L would also maximize log L, and we would obtain the same answer. But it would be easier to maximize log L, hence we'll take the log of this function. So it would be nothing but sigma I is equal to 1 to n log of yi times log of sigmoid of w transpose xi plus sigma I is equal to 1 to n 1 minus yi log of 1 minus sigmoid of w transpose xi. So we have to maximize this, or we can say we have to minimize the negative of this. So minimize minus log of L, and minus log of L is nothing but sigma I is equal to 1 to n yi times log of sigmoid of W transpose xi can be written as probability of y is equal to 1 given xi minus sigma I is equal to 1 to n 1 minus yi, and this is nothing but probability of log of probability of y is equal to 0 given xi, or we can say log of 1 minus probability of y is equal to 1 given xi. So since we have to minimize the negative of log of likelihood, we can consider this as our loss function that we want to minimize, and hence this function here is the loss function which we use for logistic regression. To get a better feel of this loss function, we can see that if yi is equal to 1, then our loss function, if y is equal to 1, then this term, second term here would be 0. Only this term would contribute to our loss function, and the loss would be log of probability of y is equal to 1 given xi. So let's say if this probability is low, let's say if this probability is 0.2, so this would be the row minus log of probability of y is equal to 1 given xi. So if y is equal to 1, we want this probability to be very high, but instead if this probability is very low, then the loss function would be very high, because minus log 0.2 is a very high value, which you can see from the log minus log x function. So this is minus log function, and we can see that this function is 0 at value 1, and at 0 it goes to infinity. So at point 0.2, minus log of 0.2 would be a very high value, and if probability of y is equal to 1 given xi is very low and yi is equal to 1, the true label is 1, but this probability is low, then the loss function is going to contribute a huge amount towards the error, and that's why the model will try to shift this probability to larger value so that loss can be reduced. So if probability is, let's say, 0.8, then minus log 0.8 would be a much lower loss value, and ideally we want probability of y is equal to 1 given xi to be 1, because our yi is 1. And similarly we can see that if yi is equal to 0, then the loss would be minus log of 1 minus probability yi is equal to 1 given xi, or which is same as minus log of probability of y is equal to 0 given xi. So basically what we want is that if true label is 0, then probability of yi is equal to 0 should be very high, or probability of y is equal to 1 given xi should be very low. So I hope now the loss function for logistic regression makes sense to you. So thank you for this video. See you in next video.